Hello, Henrietta.
Hey Oliver, how are you?
Good, how are you? Great to see you again.
Me too. I'm
Are you still in
sad to
Gathertown,
miss out
Oliver?
on the frisbee and soccer and hiking, but
Yeah. So I just left Gather Town. Ethan is there and he's going to make an announcement in just a few seconds for everyone to come back.
okay.
Great.
I keep hearing this ding dong. Does anyone know what that is?
I believe it's whenever someone joins the meeting, or there's a different ding dong when anyone leaves.
Okay.
There's also one for messages on Gather Town. Might be
Okay.
that.
I quit Gather Town at the moment, but yeah, I don't know, Alex, if it's possible to maybe not have, if that's a setting that we could turn that off. I don't know if that would be you.
Yeah, I'm fairly certain there is, because I never had it in any of the meetings that I hosted for my TAing last year. There's also, I sent you an email. I think it might also be good to turn off the this meeting is being recorded thing, because I always feel like it's interrupting someone when it starts.
Yeah, good. You sent that to me and Ethan. I think it may be Ethan
Yeah.
do that, and I'll
Okay.
ask him to see if he can also turn off the ding dong for people joining.
But we're not hearing the ding dong. I think it's just
It's only the yeah, it's just hosts.
Oh, okay. Okay, so I can if it's just the hosts, I can endure it. That's
I've disabled it anyway.
oh, okay.
We
Thanks.
don't need
Oh,
it.
cool.
I don't know about the recording notification. I'll look into that.
Okay, cool.
So I was thinking, certainly we're not scheduled to have another coffee break immediately after this. So we'll certainly want to have questions for Henrietta here on Zoom after this. And people can go to Gather, but it's not like an official scheduled time. But so we can have some Zoom questions.
Yeah.
Okay, I guess it's time. People are mostly back. Tom or Veronica, do you want to introduce Henrietta, or I can introduce her anyway?
I can do it. Okay, we're very happy to have Henriette Elvang from the University of Michigan. She's going to be giving a series of lectures on scattering amplitudes. Take it away.
All right, thank you so much. Thank you for the invitation. And to all the students out there, I'd love to play frisbee with you, but we'll have to wait for another time to do that. So I'll be giving lectures here about scattering amplitudes. I'll encourage you to interrupt with questions anytime, and I look forward to talking with you after the lectures in any one of the formats that are available. Okay, so let's get started. In a traditional QFT class, you learn how to write down Lagrangians, and you know how to extract those Feynman rules from the Lagrangians. And using the Feynman rules, you can compute scattering amplitudes. You learn about symmetries and that you can do infinitesimal transformations of the symmetries, and there are symmetries when that infinitesimal transformation gives you some total derivative of the Lagrangian. And those symmetries will then imply ward identities on the amplitudes. And so in your QFT class, you learn about trees, and you learn about loops, and you learn about renormalization, and you may learn about effective field theories and so on. So you learn all sorts of good things. But the thing that you're typically not taught is how to go backwards. So what do I mean by that? I mean, in a sense of starting over here with the amplitude and somehow making it back to the Lagrangian, or even just to learn more about what space of theories exist. So one of the more modern approaches is to take as the starting point, not so much a Lagrangian, which actually suffers from lots of redundancies in many settings, but to start and focus on the physical observables without direct reference to Lagrangians or Feynman rules. That way you can construct the physical observables, knowing something about their analytic properties, and you can then use the amplitudes as the physical observables to examine the possible space of theories. So for example, if somebody brings you a spectrum of particles and say, I'd like to understand what kind of theory exists with this spectrum of particles and the following list of unbroken symmetries and the following set of spontaneously broken symmetries, and maybe some duality symmetries on top of that, what exists? Then the traditional approach would be to go to the Lagrangian and try to write down something that works, something that has fields for that spectrum of particles, something that has some operators and interactions, and perhaps you find something that works, perhaps you don't. If you don't, then the question is it just that we didn't try the right thing? Did we mess up something? Did we not get the right insight? And if we do find some theory that has the properties that we wanted, then do we really know that it's a unique theory, or is it possible to do other things? We might even find two Lagrangians that look really different, but they might even describe the same physics. So there's a lot of redundancies in the Lagrangians that may not be so obvious. But the power of starting here with the physical observables and going backwards is really that we can characterize cleanly, do theories exist or not? And especially the not is something that these theories are very good at. So I'll illustrate this to you. And the overall goal with the lectures here is to give you an introduction to these modern amplitude methods and show you a selection of applications. I won't be able to cover everything. I won't be talking a lot about all the exciting frontline stuff that is happening, because then I'll just be talking. I want to actually show you something and show you how to do things. So here's the plan. A lot of times in Amplitudes lectures, the material gets front loaded with a lot of technical stuff about spinor formalism. And I'd like to avoid that in lecture 1 and simply focus on scalar theories. That will build the foundations for us for what we'll need in later lectures. And then tomorrow we'll talk about particles with spin and talk about spinor formalism and how powerful those methods are. And then in lecture 3, I'll talk about solved theorems. And in lecture 4, we'll talk about the double copy. Okay, so let's get started. And since we're starting with scalar theories, I'm going to start with something that you have seen before. So here is a Lagrangian right there. And here in the beginning, I've pre-written a little bit of stuff just to save a little bit of time when it's stuff that is sort of review or a lot of text, but soon I'll start writing in real time. Okay, so here's our Lagrangian. It has a kinetic term. It has a cubic interaction, a quartic interaction, a quintic interaction, and then you can write down whatever you want. If I start with this action and I start computing my 3-level scattering amplitudes, then the 3-particle amplitude can of course only have a contribution from the cubic vertex, so it's just a constant. The 4-point amplitude has contributions from the pole terms. So here's one example with the 1-2 channel, and then plus all the permutations of inequivalent diagrams, plus the local contact terms that comes from the 4-point interaction phi to the 4. If I write out what this is, I can write it in terms of Mandelstam variables. I'll call them Sij, and they'll be Pi plus Pj, all of it squared. Here, I haven't put in a mass term, but you can, of course, just do that too. Okay, so we have these pole terms. They're called pole terms because they have simple poles. Then there are the 5-point interaction. Likewise, we have diagrams that involve the cubic vertices. And we have a class of diagrams that involve 1 cubic vertex and 1 quartic vertex. And of course, we can also have the contact term that comes from the phi to the 5th interaction. Okay, standard field theory stuff. We can write down what those diagrams are. There are 2 poles in the diagrams with just cubic vertices. One of them is illustrated here, and just a single one from the other one. Okay, so why am I doing this? This is stuff that you know from your QFT class in the first semester. The one thing I want to emphasize first here is that 3 amplitudes are rational functions, and they have simple poles. They cannot have double poles. They do not have logarithms. They do not have any sort of weird fancy stuff. They just have simple poles. And those simple poles are located precisely where the physical amplitude, where the physical particles can be exchanged. Now, let's take a look at what happens on those poles. So let me try to go to this 4-particle amplitude. And I'll multiply it with a Mandelstam variable S12 that we normally just call S. And then I'll set S12 to 0 in order to compute the residue on that pole. So when I multiply in here, I'll pick up the residue, which is just the cubic coupling squared. And so I see that the cubic coupling, well, that's just a product of 2 3-particle amplitudes. Let's do the same at 5-point. What do I get? I multiply by S12, and you can see that I will pick up from diagrams of this form here, with the lines 3, 4, and 5 permuted in all inequivalent ways, I will pick up something from that pole, and that's going to be another pole term, and there'll be precisely 3 of these because there are 3 different choices of which line goes right here where the 5 is. It could be 3, 4, or 5, and all of them will share the 1, 2 pole. So I'll get lambda 3 squared times 1 over s 3, 4 plus 1 over s 3, 5 plus 1 over s 4, 5. And then I'll also,
Henriette, sorry,
yes,
just super quick question. Will these notes be posted?
yes, I'll post the notes afterwards. Yep. I also posted some references already on the wiki page for the first lecture here. But yes, I'll post the notes afterwards. Great. Then I'll also pick up a pole here, and that will take the value of lambda 3 times lambda 4, and none of the other permutations of this diagram right here will give you a pole in the S12 channel. So this is really all you get. But if you rearrange this, you would see that this is actually lambda 3 times a 4-particle amplitude with momentum labels 1, 4, and 5. So I can rewrite this as A3 with momentum 1 and 2, and then I'll call this minus P12. And then it multiplies a 4-particle amplitude with momentum labels P12 for momentum conservation 3 and 4 and 5. Why do I go through this? I go through this to emphasize that amplitudes on these simple poles are not just where the physical particles are exchanged, but in fact, they're precisely such that they factorize into lower point amplitudes. This is a really important property because this is what underlies how you can do these famous recursion relations that allow you to construct higher point amplitudes from lower point on-shell input. It's the knowledge of where the poles are and what the residues are on those poles. And in fact, this allows us to construct the tree amplitudes from knowledge of 2 parts, the pole terms and parameterizing the possible local terms that could appear. And again, this is really what underlies the idea of recursion relations, and they go on the various names. There's some known as BCFW. There are versions of this that are called online shift. There are some more recent ones called soft recursion relations and so on. So let me pause for a second to see if there are any other questions.
What do you mean by the local terms? You mean just the contact term?
Very good. So I meant the contact terms. So sometimes locality is used in 2 different ways, or actually in multiple different ways. One way of saying locality is that we think about the Lagrangian as being local. It doesn't depend on, we don't allow the fields to lie at 2 different points in space-time. We don't have things like 1 over box appearing in the interactions. So the interactions are really strictly local. What that translates into for amplitudes is a locality statement, which means that it has only poles in the correct physical places. But sometimes by local, we also mean the things that come from the contact terms, in the sense that the parts that don't have poles. So it's used a little bit ambiguous, but the locality of the Lagrangian translates directly into properties of the amplitudes, poles in the right places plus polynomial terms.
Okay, thanks.
Great. Excellent.
Can I ask a question too?
Absolutely.
So does this mean for non-tree? Let's see here. Sorry. Is it for planar? This recursion only applies to planar diagrams?
There's nothing. Oh, well, so everything that I'll talk about today here will be about tree amplitudes. Actually, most of the lectures will be about tree amplitudes only. And that's when the statement that they're rational functions with only simple poles really enter. Once we have loops, the analytic structure becomes much more interesting and also more complicated. So there can be logarithm, branch cuts, dilogarithm, polylogarithms, all sorts of things can start appearing. Still there, you can have a lot of control, but that is not from just poles, for sure.
Thank you.
Cool. When I say local terms, and that refers to the other question before, sometimes I also refer to the matrix elements. So if I have some operator, there would be a matrix element associated with it. What it mean by that is the amplitude that comes from just calculating the Feynman rule on shell for that particular operator. Okay, Now, we might say, great, now we talked about field theory for, 15 minutes or so. That's it. I covered all of scalar field theory, right? What are we going to do for the last hour? Well, there's a lot more to say, because there's also effective field theories where we can think about derivative interactions. And so what I'll do now is something that is in some sense a really, really dumb and trivial example. So be patient. I have a point in doing it because I want to use it to illustrate some of the mechanisms that we use and makes the on-shell methods really powerful. So we're going to look now at derivative interaction for scalar field theories. And so we'll start again with your familiar area of on-shell Lagrangians. And so I have a kinetic term for my scalar field. And now I'm going to add some funny term, which looks like this. So there could be other interactions too, but let me just add this thing. Now, what's the Feynman rule from this? Well, you know that derivative translates into I times momentum. So up to some powers of i's and minus signs and so on that we'll not worry too much about, this quartic interaction will give us a Feynman rule that is basically proportional to the coupling. Maybe there's some minuses, maybe there's some i's, maybe there's some conventions. We won't worry about it, but it'll give us translation into contractions of momenta, because these two derivatives are contracted in all possible ways. So you have to do plus dot 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 here means all the permutations of which lines have the derivatives and adopt the derivatives. Okay, so there's a Feynman rule and it looks like that. Now, if I want to compute the 4-particle amplitude, I have to take the particles on shell. Here I have massless particles, so each one of them has an on-shell condition on it. It squares to 0. And so when I take my Feynman rule here and I take all the lines on shell, I can regroup every term into 1/2 P1 plus P2 squared. And then I have to subtract off, of course, and let me just write it explicitly so you can see it. Plus all the terms. So this particular term translated into all of that stuff. And because my particles are on shell, these two squared terms are 0. And I'm left with just 1/2 S12. And so if I add up all the terms and all the permutations, what I end up with is S12 plus S23 plus S13. And you might recognize this as S plus T plus U, when, because I have massless particles only, is equal to 0. So here, the 4-particle amplitude was 0. Okay, that was a really boring example. I told you that. I told you it was a trivial example. But why is it 0? So let's understand why A4 here was 0. And then of course, I'll come back to the modern way of maybe seeing this from the point of view of the amplitudes. Okay, so let's do it first in one way. When I have an interaction that looks like phi squared, d squared, phi squared. One way I can rewrite this is to use the fact that I only have one scalar field. And this is the same as 1/3 d phi cubed times contracted into d phi. All right, so what? Well, this sits inside a Lagrangian, which is integrated to give me the action. And so I can use partial integration or integration by parts to rewrite this in terms of a total derivative. Well, actually, we can just think about that this is integration by parts, or we can just think about it as a direct rewrite. So let me just do the rewrite. I can write this as 1/3 d of phi cubed, d phi phi. This is the total derivative. And then I have to subtract off the other part here. 1/3 phi cubed box phi. So why did this happen? This part here is a total derivative. So sitting inside my Lagrangian, assuming fields fall off fast enough far away at infinity, that vanishes and that doesn't contribute as a total derivative. And this part here, that vanishes by the leading order equations of motion, which says that box phi is equal to 0. So what's the connection between this weird manipulation that I just did to just illustrate, or a trivial manipulation I just did to rewrite this term as something that obviously cannot possibly contribute to an on-shell amplitude. So this is why it doesn't contribute. It's a total derivative plus something that vanishes by the equation of motion. Well, the connection is the following, that equation of motion box phi equal to 0 is equivalent to the statement that all of the particles are on shell. So Fourier transforming box gives me p squared, that is 0 from the on-shell condition. That's equivalent to the equation of motion statement that I used to rewrite the operator. And the total derivative, what does that do? Well, if I do the Feynman rules on a total derivative term, this derivative basically ends up touching every one of the fields, and it does so in the same way. So this is necessarily proportional to something that will vanish by momentum conservation. And so this part of the derivative, this overall derivative, will necessarily give me something that is P1 plus P2 plus P3 plus P4 mu equal to 0. Okay. So what was my point in illustrating this? It was to say that even if there is a non-vanishing Feynman rule, the on-shell amplitude is 0 because the operator really vanishes on shell after partial integration or integration by parts. Okay.
Could I ask a question?
Yes.
Is this something like this term can be removed by a total derivative? Sorry, by a field redefinition or something?
That's exactly what I was.
Sorry.
Excellent. So thank you for leading me into that. Another way of saying this would be to say that the operator I wrote down in my Lagrangian could be removed by a field redefinition. And if I take phi and I replace it with phi plus some constant alpha, phi cubed, then that means that d phi goes to d phi, plus 3 alpha phi squared d mu phi. And then we compute d phi squared as our kinetic term was, then you'll see how this turns it into the usual d phi squared. And then from the cross term, you'll get 2 times 3 alpha phi squared d phi squared plus terms that are order phi to the 6th power, which I won't worry about for now. And so you can simply just choose your alpha, that constant in the field redefinition, to be our G4 divided by 12, and that removes this interaction that we had up there directly. So another way of saying it is a term whose on-shell matrix element vanishes can always be pushed by field redefinitions into higher points. So for this case, it's a trivial example. Some of you might have done that.
Can I ask you?
Go ahead. Yes.
Saying that.
Sorry, I couldn't hear you. Your voice was breaking up. I couldn't hear the question. Maybe you can write it in the chat and I'll come back to it afterwards then.
I think he's frozen at the moment, so.
Okay, so we'll carry on and come back to the question. So again, that was an important point, that the lessons I want to draw from here is that amplitudes are invariant under field redefinitions. Of this type of field redefinitions. The Feynman rules are not, but the spirit of this will be, who cares about the Feynman rules? We'll carry on. And I think this is an important point. Sometimes it's said that the amplitudes program gives you important simplifications when you have gauge because of gauge invariant, but there's no gauge here, there's no fancy stuff. It's just scalar theories, just scalar effective fields. And of course, this is a rather trivial example, but it illustrates explicitly the ideas that, again, if an operator has a vanishing on-shell matrix element, I can push the information from that into higher point. Perhaps I can even push it completely away if it's a trivial operator like this one. Okay, so this is another reason why using amplitudes can be a way to distinguish theories that might look very different, especially effective field theories, because the operators look very different. But if they have the same observables, they're really the same theory. Another thing it can do is to help you characterize the local operators, because it gives a clean way of distinguishing whether they're independent of each other under integration by parts and use of the equation of motion. All right. Cool. So the on-shell methods will avoid Lagrangian ambiguities related to, and here I'll mention the field redefinitions, partial integration, and equations of motion. And in general, also for things that are not scalar, it will avoid issue of gauge invariance. And then I can see the question from Suman, which is, can we remove all two derivative higher point contact terms? So for a single scalar theory, yes. For scalar theories with more structure, like a color index, or for multiscalar theories, no. And we'll see examples of this coming up shortly. Very good. Okay. So good. So another thing that came out of this example was like, how do these things enter for this list of properties that we can avoid when we work with the amplitudes to enter? The field redefinitions we get rid of because the amplitudes are simply manifestly invariant. The partial integration translates into momentum conservation that will always impose. Equations of motion is the on-shell condition for the external states. And gauge invariance that will enter basically later at the same level as field redefinitions. The amplitudes are manifestly invariant, so we'll avoid those ambiguities. And so these actually give very powerful characterizations. So let's now see how we would approach characterizing scalar field theories from the point of view of just the amplitudes. So we can ask the question, what can an endpoint amplitude with n identical scalars possibly be? So that's the question. And so now let me just run through the list of properties it should have from the point of view of the Lagrangian versus what it means on the amplitude. So I'll have
Sorry,
Lorenz.
can I interrupt?
Yes?
There's a question in the chat. I think it might be the person who was cutting out earlier.
Yes, and I think I answered that.
Oh, you did? I'm so sorry.
That's all right. No problem. Keep me up to speed doing that. So Lorentz invariance means that whatever I have with Lorentz indices have to be fully contracted. In a scalar theory, at most, I can have a 4 momentum or a d momentum, of course. And so that means that the amplitude, so this is Lagrangian, this is amplitude. The amplitude depends on Mandelstams only for scalar theories. Okay, then I have the statement of locality that we mentioned briefly before. That means that a term in the absence of 3-point interactions will have polynomial terms in these variables. So they're polynomials. We have, of course, that these are subject to momentum conservation. And that comes out, of course, translational invariance in our Lagrangian. Then we shouldn't disregard a simple thing like dimensional analysis. What is that bias? Well, a simple aspect of it is that the mass dimension of an amplitude will always be 4 minus n. That comes out of the cross section having the right dimensions. So this is the mass dimension. Oops. And we can also see that if we have an interaction with 2 n derivatives in it, and say k scalar fields schematically, then this means that it will have a matrix element that is a degree n polynomial in the Mandelstams Sij. Okay. And then number 4 is Bose symmetry. Since I said here that I had n identical particles, then it must be that the polynomial, my n degree polynomial, must be symmetric in identical moment in the momentum labels. So what this does is that it translates the problem of constructing scalar Lagrangians into a problem of constructing polynomials in Mandelstam variables. And the latter is much, much simpler.
Can I ask?
Good, go ahead.
What do you mean in the absence of 3-point for point 2 for
Oh,
locality?
I just meant that when I have free particle interactions, actually, maybe I should say this a little bit differently. So let me say that local endpoint operator, if I make that put on the Lagrangian side, whoops. Let me put that here. That's the thing that translates into a polynomial. But of course, in general, the amplitude need not be a polynomial because it can have pole terms. But those pole terms I can understand from the factorization. So this is what helps me characterize the non-polynomial pieces. So thanks for asking that.
Thanks.
Cool. All right. So let's do some examples. What can an amplitude possibly be at 3-point? Well, it could be a constant. We've already seen that. And then the point is it can be nothing else. Absolutely nothing else is possible. Not a tree level, not a loop level, nothing else it can possibly be for a scalar amplitude. And the reason is that the only thing it could possibly depend on would be Mandelstams, but there aren't any Mandelstams at 3-point because of the on-shell and momentum conservation condition. These all vanish, as I illustrate here. So this is really all it can be. And so that was a little bit what I had in my head before. I was thinking about 4-point. In the absence of free particles, there aren't any poles. Everything is just polynomial. But of course, at higher point, the pole terms of 4-point and so on can come in. Great. 3-point, that was easy. Let's move on to 4-point. Well, there can be pole terms. We already discussed those, so let me not write them out. Then we can have a constant. And then the next thing we could possibly have would be a first order polynomial in the Mandelstams, a symmetric polynomial. And the only thing it could be to be symmetric would be s plus t plus u. But you know that this vanishes by momentum conservation. So this is ruled out. And that was exactly the example that we saw. The two derivative term could be removed by field definition or simple partial integration and equation of motion. All right, what next? Symmetric polynomial that is quadratic in ST and U, that's fine. That's non-zero, that exists. What else? Next order, cubic polynomials. And now you can think that this is getting so boring that you can go do your laundry and whatever, but I'm going to write down a few more terms. Just because I can and because I want to show you something. I'll keep going. Are you bored yet? Just writing and 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 writing. Oops, there was something new. So this I just did to illustrate to you that while you might get the idea that there's a unique symmetric polynomial in ST and U at all orders, this is actually not the case. These two are both order p to the 12th. So you actually have to do the calculation and characterize what is there. And you might go back and ask, what is the difference between these two polynomials in a Lagrangian level? And so let's just try to figure that out. This one would come from a term that looks like phi squared, and then 6 derivatives across contracted. That would give an order p to the 12th term. Whereas this guy here comes from a different type of operator, where I put 6 derivatives on one field, and then I put 2 on each of the other ones. So now you could imagine that you could do something similar with the lower point terms, like the 5th order polynomial, 4th order polynomial. You can try all different arrangements of these indices, of these derivatives and their contractions. And no matter what you do below this line at lower order, 10 powers and momentum or less, there's just only one choice you can have. But starting at 6-point, there are 2 different operators. And it might be a little bit non-trivial to see in your usual sense that these 2 are really independent under partial integrations and equations of motion, but that is the case.
Hi, sorry, just one question.
Yes.
A fourth, yeah, that's a question that's also in the chat. Why don't we have an STU term without the squares?
That was just what I wanted somebody to ask. Thank you for asking that. What about up here? For this order here, at order p to the 6, I could have had an STU. But the fact of the matter is, and you can see this by substituting in u equals minus s minus t, that these two things are actually exactly the same up to a factor of -3. So by momentum conservation, those two are not independent, which means if you try to write down an operator with 3 derivatives on one phi and one of each of the other ones, you can convert that into one of this form here with 3 derivatives self-contracted across for the 2 different fields. You could convert those into each other by partial integration, and you can try to do that exercise. It's a fun little thing to do.
The same is true for ST plus TU plus US. Is that?
That what, sorry?
There's also ST plus TU plus SU, right?
SU plus TU plus good, so plus
ST.
ST. That is also symmetric, but if you plugged in again u equals minus s minus t, you would find that that gives the same as the quadratic polynomial up here, this one. And so you can simply go through the list and try all things that you can think of to do these, to try to circumvent what I just said to do this. Another little exercise you could do is that you could say, in fact, you could have either 2 or 1 up to quite high order. If you go to order p to the 24, it turns out that you have 3 independent terms. How high do you think you have to go up to get 4 independent terms? Well, hard to guess. It turns out to be p to the 36. Not so much a phenomenological application, but just to illustrate to you the idea that if you had to put 36 derivatives on 4 fields, it's a little hard to sort of wiggle your way through and figure out how many independent contractions you can do under equations of motion and partial integration, when you can just write a nice little mathematical code that tells you how many there are at any given order. Okay.
Can I ask a question?
Yes.
And maybe it's kind of naive, but how much does starting with the amplitudes buy you? And like, it seems like you're trying to get past all the redundancies, making field redefinitions and all this stuff, but then even now writing down the amplitudes, you have to make sure that you're not writing it down anything redundant, like under the different identities and stuff.
But so that's exactly what I wanted to emphasize. That the lesson here is that it's really easy to characterize Mandelstam polynomials under a certain constraint, which is momentum conservation in this case, versus trying to move derivatives around. If you wanted to write a mathematical code that was doing this, it's much harder to encode up integration by parts and the rules for this than it is to just code up Mandelstam polynomials. So it's very easy to deal with polynomials. It's very messy to deal with integration by parts. That's sort of the lesson. By the way, there's a nice, if any of you are very mathematically inclined, one way you can think of this construction is a polynomial ring. So this is an aside. You can think of a polynomial ring in the Mandelstam variables, and then you basically mod out an ideal that is generated by the constraints of momentum conservation. That gives you a polynomial ring modded out by this ideal. And there's a technique called the Gröbner basis that allows you to find exactly the independent polynomials. And mathematicians have a program called Macaulay that you can use to code this up if you want to. So that's a fun little aside. It can be useful in some contexts. So these techniques are very useful for a wide range of things. Let me mention some applications when you also include, say, masses and spins. These techniques are starting to be more widely used in characterizations of standard model effective field theory to characterize the operators that exist there. And you can also use them to characterize the higher derivative operators and contributions in, for example, super Yang-Mills theory on supergravity. These could be high derivative contributions, for example, from alpha prime corrections in string theory. String theory, or assessing when the first UV divergences could possibly occur in, for example, things like supergravity. And this becomes just even more powerful once you have particles with spin, as we'll talk about in lecture 2. Okay, so far we just talked about polynomials and scalars and so on, single scalar field. Of course, I can have multiple scalar fields. And another thing that you often deal with is symmetries. So now I want to talk about symmetries. The first context will be unbroken symmetries. And as we talked about in the beginning, a Lagrangian, you can think of that as has a symmetry when under variation, it's at most a total derivative. And that gives word identities for the amplitudes. So an unbroken symmetry gives you a word identity. What that is a very fancy word for some linear identities among amplitudes. So let me just illustrate it in one example. For example, if L has a global U1 symmetry, then that translates for the amplitudes into charge conservation. And so say that I have some complex scalar Z, there's some U1 rotation on it and the opposite for the complex conjugate. That will then translate into amplitudes will vanish unless the number of particles with charge plus and minus is the same. Okay, so a familiar example from electromagnetism and so on. There are actually also duality symmetries. Let me not talk so much about that. In that case, L does not have the symmetry, but the equation of motions do have that symmetry. And this translates into some similar word identities for the amplitudes. An example of this would be electromagnetic duality, which we may talk a little bit about later in the last lecture. Okay, then the other class of symmetries I wanted to talk about is when you have spontaneously broken symmetries. So this is the situation when you have something that is a symmetry of your Lagrangian, but not of the vacuum. And for the amplitudes, that translates into a different kind of word identities, which are known as soft theorems. So, for example, if I have some spontaneous symmetry breaking of a group, and here I'm thinking about global symmetries, so some group that is spontaneously broken to some subgroup H, then I have Goldstone bosons for every broken symmetry. So the number of Goldstone boson equals number of broken generators. And the number of broken generators is the difference in dimension of G and H as groups. And this is also the dimension of G over H, that coset. Now, basically, these Goldstone modes actually live in that coset. So the Goldstone scalars, they belong to that coset. Okay, Now, what does it mean at the level of amplitudes to have Goldstone modes? It means that if these Goldstone scalars, let's call them phi, just as there are other scalars, if I compute an amplitude with them, not just with themselves, but also with other things, then they have a property that when I take any one, and the Goldstone momentum to 0, I'm going to scale it to 0 by some parameter epsilon. I can do this because the Goldstones are exactly massless. Then the amplitude will behave in a certain way that in some cases is 0. So it will scale with epsilon. And what the sigma that I wrote here, this is sort of the degree of softness. And if I have internal symmetries broken, by the way, I'm not talking about the Higgs mechanism here at all. We're just talking about breaking of internal symmetries. Then sigma is 0 or 1. And 1 is a very interesting case because this is something what is known as an Atlas 0. It is an Atlas 0 in that when sigma is greater than 0, then the amplitude will necessarily go to 0. If I have translational symmetries broken, like translational invariance spontaneously broken, and we'll give a context of that later, that will give me sigma equals 2. So that actually means that the amplitude vanishes faster. And I hope I'll get to say a little bit at the end of today of why that is. But these are examples of it. You can derive soft theorems for the Atlas zeros under assumptions that rely on this coset group being a symmetric group and the absence of cubic interactions that give you sigma equals 1. But the general statement is that you can also have sigma equals 0 and other particular soft theorems that relate to those. So one question we could ask now, coming from the bottom up, we say we don't know anything about G and H and particles or whatever Lagrangians these might have. We can simply ask the questions, what scalar theories exist that have vanishing soft theorems?
Just to clarify, vanishing soft theorem means sigma equals 1 or 2.
Then yes, I mean sigma greater than 0. Exactly, good. And also here, I'm only taking one momentum soft at a time. So any one of the Goldstone momentum, I can take one and I can ask what softness degree that is for each kind of particle, if I have more than one. There are also multi-soft scalar theorems, and in particular the double soft theorems are important, but I won't talk about those here, just the single soft theorems. So which scalar theories exist with vanishing soft theorems? And specifically, that means sigma greater than 0. So let's now analyze this question. First, let us observe that if I have a non-vanishing 3-particle amplitude, that means, and let's call this non-vanishing 3-particle amplitude something that has a coupling lambda. We know that that's the only thing a 3-particle amplitude can possibly be. Then this implies that the 4-particle amplitude, already this doesn't look like it would vanish, right? But 3-particle kinematics is a little subtle. So let's just put a nail in the coffin for real. Then the 4-particle amplitude has its poles. And it's clear that as I take, say, momentum 1 to 0 or any of the other one, this diverges. So in a certain sense, this has sigma equals -1. Now, theories with negative sigmas are very important, and that's what we'll talk about in lecture 3. But for now, we'll talk about things that have positive sigma. Okay, so in order to have a soft vanishing theorem, having sigma positive, I need the 3-particle amplitude to be 0. Good. So now we move up to 4 particles. Thankfully, we already characterized our 4-particle amplitudes. So we can go and we can see what we have. If it's a constant, then that will be associated with sigma equals 0. So we throw that away. Then we knew that at the linear level in Mandelstams, it's vanishing for kinematic reasons. So we throw that away. So well, there's nothing to throw away. And then we can go ahead and we can look at G4 prime. Let's give it its own name. Let's just call this thing G4. Get rid of this other part. That's just some number. G4 S squared plus T squared plus U squared plus dot dot dot. Now this is very nice because if you look at this and any one of the momenta I would take to 0, it's symmetric in all of them, so I can pick any one of them. Then I see that not only does this go to 0 with sigma equals 1, it actually goes to 0 with sigma equals 2. So it's even better than just having a positive sigma. It's sigma equals 2. Okay, so I have something that is the lowest order I can work with. So let's stick with that and take a look at what happened at 5 point. Well, at 5 point, again, a constant term won't cut it. That would have sigma equals to 0. The next term I could imagine writing down would be the sum over all Mandelstam variables. And what happens with that is that that's 0. The next thing I could write down with some G5 would be all the Mandelstam summed up squared. And that turns out to be the only thing that you can have at that order. And when I take, say, P1 to 0 here, then I get something non-vanishing. Then this whole thing becomes S23 squared plus S24 squared, etc. And this thing is non-vanishing. So this has sigma equals 0. So I would have to go to higher order in order to get some sigma that is positive. And since at 4 point I already had something at 4 derivative level, I'm just going to stick with that and go on to 6 particle level now. So what happens at 6 particles? Well, now I have to take into consideration that I have 4 particle interactions. Plus permutations. And then I can also have the local polynomial terms. Sometimes we would call those the local terms. Okay, so what are those? Well, we don't know anything about Lagrangians. We don't know anything about Feynman rules. So I'll simply just compute things that have the right poles and factorize into the right things. So let me just write down what I get from the diagram here. On this side here, on the left side, I have a 4 particle amplitude with momenta 1, 2, and 3. So I know that that 4 particle amplitude that I'm interested in comes from this term up here. So it's going to be S squared plus T squared plus U squared with the correct momentum labels. So I have S squared, that's S12, I have T squared, and I have U squared. And then on the other side of the diagram, I'm going to have the same, but with 4, 5, and 6 labels. And then the pole comes from S1, 2, 3, which is the same as S4, 5, 6. Let me write it that way. Then plus all the permutations of inequivalent diagrams plus polynomial terms. Let's call those poly6. Okay. What happens when I take, say, momentum number 6 to be 0? Well, I look at my term here and I see that nothing happens to the part that involves momentum 1, 2, 3. But up here, these two terms both go to 0 when P6 goes to 0. And I also get rid of momentum label 6. And then a nice little cancellation happens, namely that the S45 that's at in the denominator cancels against an S45 in the numerator. And in fact, I end up with something that is manifestly local. In the sense that it doesn't have poles, something that is manifestly polynomial. That's very nice, but it's not 0. So what's going on with that? And when I add permutations, as I should, it's still not 0, as you might have hoped. So maybe you feel that this dooms any theory of this kind to even have sigma equals 1, because the pole terms did not give 0. But the pole terms did give something that was polynomial. And so perhaps I could find a polynomial term in the Mandelstams that would cancel this term. So let me see what actually exists. So if I look at the polynomial terms, what can they be? We can go systematically. This guy, I can't have a constant because that would have sigma equals 0. I'm not interested in that. There's no linear term. The quadratic term does not have sigma equals 0, but at the order that we're actually interested in, namely the order of momentum to the 6, which is what this is, there are 2 independent terms that I could write down. So let's call them lambda 6 times S12 cubed plus all the permutations that this can have. And then there's a separate one that we can call lambda 6 tilde, which is S12 S34 times S56 plus all the permutations it can have. And those are the only 2 operators you could have, and they can correspond to 2 different index contractions of 6 derivatives on 6 scalar, 6 derivatives on 6 scalar fields. Okay, now here's the nice thing. When P6 goes to 0 here, this goes to something that is non-zero. But you see the other terms in this part here, they will necessarily go to 0 as any one of the momenta goes to 0, because the momentum is represented everywhere, and they go to 0 at order sigma equals 1. And this one we could call sigma equals 0. So what you have to hope is that somehow you can use this polynomial here to cancel whatever came out of the softness calculation there. But they don't look the same at all. However, because there are only 2 independent polynomials at 6-point order that are fully symmetric in all the variables, it actually turns out that the nice thing does happen. That the thing that this will go to on the permutations is the following. So when I do the permutation up here, I can actually find that this polynomial plus all its permutations of labels 1, 2, 3, 4, and 5, that precisely gives me the polynomial S12 cubed plus all the permutations of all the labels in terms in 1, 2, 3, 4, 5. And that's exactly what this will give when you take the limit of P6 going to 0. So what is the upshot? The upshot is that I can get this 6-particle amplitude with its pole terms plus its local term to go to 0 as epsilon to the first. In other words, it has sigma equals 1 when I pick the coupling that sat in front of these things here. Well, let's actually put in the couplings so that we know what it is. This was G4 squared, that's sat there. So all I have to do is to pick lambda 6 from up here to be equal to G squared. And that's then what we have achieved. I mean, at least up to a sign, which I didn't probably work out. I may have to pick it to be minus this value. That sounds appropriate. Okay. But one thing that we then notice is that this leaves lambda 6 tilde completely free. And when lambda 6 tilde is completely free, we haven't fully fixed the theory. There's a free coupling at 4-point. There's lambda 6 that was fixed in terms of that, but then there's lambda 6 tilde that is left entirely free.
Can I ask something?
Go ahead.
They're giving different value of sigma, right? Like from A4, you got sigma equals 2, and the 6-point amplitude gives sigma equals 1. So
that's right. So you're anticipating the right thing. So sigma 1 does not fix the theory. It has an ambiguity left in what is the value of sigma 6 tilde. But then we could go back, as it was just pointed out, we could go back and say, actually, our 4-point amplitude has sigma equal to 2, maybe we could push things a little bit and get a cancellation between the subleading term at order sigma 1 that came from the soft limit of the pole terms and the cancellation of that local term and that new term. And that is indeed possible. So indeed, it is possible to get A6 to go as epsilon squared. In other words, sigma equal to, by choosing lambda tilde 6 to be some number times G4 squared. And this is indeed quite nice. Now we have a theory with this very enhanced soft behavior, and we found that at 6-point, it was completely fixed in terms of 4-point. Likewise, it turns out that 8-point becomes completely fixed in terms of the 4-point. If you did the same at 10-point, it would be completely fixed in terms of that at 4-point. So in fact, at any n, the model with sigma equals 2 and a single scalar field is uniquely fixed. That seems like it should be some kind of special theory. So you might want to go back and see what does this mean in terms of a Lagrangian. Now you can reconstruct the Lagrangian based on the amplitudes. So let's see what it is. We assumed a standard kinetic term because that was our standard propagator. And now I'm just going to set this 4-point coupling to 1 just for simplicity, but you could have kept it. Then if I write my 4-point interaction, it turns out that in order to get this number right here, G4 to be 1, that you require a factor of 1/8 that sits in front of d phi to the 4, and that will then generate the correct 4-point amplitude. Then to generate the correct 6-particle amplitude, you have to write 1/16 d phi to the 6. To get the correct 8-point amplitude, you need 5/128 d phi to the 8th, plus ... Perhaps, or perhaps not, this looks familiar to people, but it's something that you can actually get in a different way. You can get it from the Taylor expansion of a very simple expression, which is 1 plus d phi squared plus 1. And this you might recognize exactly as the dpi action. So the Dirac-Born infeld action is in fact the unique model that has sigma equals to 2. And then you might ask, why does it have sigma equals to 2? Well, so the DPI action describes the low energy effective action on a brane. And the low energy effective action sort of describes the wiggles of the brane in the transverse direction. So it has some transverse direction. And in that transverse direction to the brane, the translational symmetry is spontaneously broken due to the presence of the brane. Now, that translational, that direction transfers to the brane. When you pull that back on the brane, that is going to be that scalar mode that lives on the brane, and that characterizes phi, our scalar, that I also wrote. Sorry, I think I'm going back between different types of phi's, but let's call it phi like this. This is the Goldstone mode of that spontaneously broken symmetry. This would be enough to characterize it to have sigma equals 1. But when we put a brane into Minkowski space, there's also another symmetry that gets broken. And that's the rotations and Lorentz boost that involve the brane directions and the transverse direction. Those mixed ones also broken. So the translational symmetry broken implies that phi has a translational symmetry with a constant that comes from this part. But then there's an additional symmetry. Let me write it like this. Plus a field redefinition. And this part, this translational symmetry, which is enhanced and depends on the space-time coordinate, comes from the spontaneously broken rotations and Lorentz boosts that involve mixed direction transfers to the brain and on the brain. The ones purely on the brain, of course, preserved for a flat brain and flat Minkowski space. And this is the part. This part here is the one that's responsible for the enhancements to sigma equals 2, whereas this part here will only guarantee you the sigma equals 1. Okay, so that's pretty cool that all this came out of just saying what theories exist with a single kind of scalar field and some soft vanishing soft limits. We discovered the direct one interaction. And I think that's a pretty cool feature. All right, so let me go back and just pose an exercise for you. Does anybody have any questions? Anything that seemed weird? Okay, me. Okay, somebody has a chat question maybe. Oh, okay, no, that's another one. So, okay, so I get to ask a question. I would like to know that up here, when we characterize local terms, I said that there were 2 independent terms, 2 independent polynomials. So there should be 2 independent operators, right, locally. But in this expansion of DBI, there's only 1 term. And that one, you can see, is the one that's actually responsible for this term here. This one matches on to that one. So whereas the local term, so to speak, that would correspond to this part, the one part that gave you a guaranteed to sigma equals 1. So exercise. Y is the only phi to the 6, not the 2 independent order p to the 6 operators. So if anybody wants to look at that and ask and talk more about it later, I'll be happy to do so. All right, so we got about 9 minutes left. So let me, in the last part, talk a little bit about other theories in the spirit of softness and vanishing soft limits. So you could ask about, what about, we got to sigma equals 2, so what about sigma equals 3? Well, there is actually a theory with sigma equals 3 that is very easy to write down the amplitudes of. And that is something that basically has S times T times U. This will go to 0 as sigma cubed whenever any one of the Mensa scales to 0. And that corresponds to a Lagrangian, which has a very simple interaction term, namely one that is d phi squared, d phi squared, and that is known as the special Galilean. Galileans sometimes arise in cosmology. They arise of studies of massive gravity, and they arise, sometimes they're said to be corrections on brains, but that's a little bit subtle because they're not necessarily compatible fully with all the supersymmetry like something like a D3 brain should have. Okay, so that's another kind of theory. So far, we sort of covered the single scalar field theories, but we could also have scalar theories with multiple flavors. So what about if I take phi in some adjoint representation, so that phi is really phi a dA, so some adjoint representation of a flavor or color group. Oh, I should mention one other thing. What about sigma greater than 3? And the answer is no, you can't do it. There are no such theories with sigma greater than 3. None. Okay, if I have an adjoint representation, that means that my amplitudes, in particular my 4-point amplitudes, say, are now decomposed in terms of the color traces. I can write them as phi A, phi B, phi C, phi D, and then I pull out my color trace. This is called a partial amplitude. And that's what people typically study when they study gluon amplitudes and Yang-Mills amplitudes and so on. Okay, so what can such a 4-point color ordered amplitude, and by the square brackets here, as opposed to the soft curly brackets before, or the soft brackets before, or round brackets, I intend to say that this is a partial amplitude. So it has the implicit color ordering in it. Now, if this comes with color ordering 1, 2, 3, 4, by cyclic symmetry of the trace, this also has to be the same as the one with 4, 1, 2, 3 by cyclicity. So what that translates into is that whatever this amplitude is, it has to be symmetric under exchanges of S and U. But it doesn't have to be fully symmetric in all the momentum labels as before. There's no both symmetry exchange now because I have a color ordering associated with it. They're not identical anymore. They have a color index. So what can A4 possibly be? Well, it could be a constant as usually, but that has sigma equals 0. So let's throw that away. And then what about that the linearized order? Now something that is symmetric in S and U, there's a unique thing, and that's T. Of course, it could also be S plus U, but that's the same as minus T. And this indeed vanishes in the soft limit and will give rise, once you adjust the 6-particle interaction and 8-particle interaction and so on, this can give rise to a consistent theory with sigma equals 1. And these theories, so there's also plus higher order, but these theories that come from this are in fact an example of nonlinear sigma models that can come from such theories. You could go to 5-point. What can arise at 5-point that has sigma equals 1? Well, there's a unique answer there. It's an epsilon contraction of 4 momenta. And what is this term in a nonlinear sigma model language? This term in nonlinear sigma model language is the West-Sumino-Witten term that can arise in nonlinear sigma models. And indeed, this has also sigma equals 1.
Henriette, you've got about 5 minutes.
Great, I'm almost there. So we can use this bootstrap of amplitudes to study exceptional theories, theories that describe things like Goldstone modes and have vanishing sort theorems. And so what I want to end with today is a diagram that shows you the possibilities. So we have actually derived a lot of this already. There'll just be a few more things to add. So on the horizontal axis, I'll put softness. So sigma equals 1, sigma equals 2, sigma equals 3, sigma equals 4. And on the vertical axis, I'll put the minus the coupling dimension. So these are negative coupling dimensions at 4-point because there's the class of irrelevant operators. So I could have 2, I can have 4, I can have 6, I can have 8. And just to give you a way of navigating, this would be 2 derivatives and 4 fields. This is 4 derivatives and 4 fields, 6 derivative, 4 fields, 8 derivatives, and 4 fields. So what did we find? We found one theory that had sigma equals 1. That was our nonlinear sigma model that I just described here at the end with the adjoint field. Then with sigma equals 2, we needed to go to 4 derivative order, p to the 4, and that gave us uniquely dBi. For sigma equals 3, there were 6 derivatives involved. There was S times T times U. This was the special Galilean with a single scalar field, single real scalar field. If you try to take a Galilean and use a complex scalar field, or you use multiple real scalar fields, it turns out that you cannot get the enhancement to sigma equals 3, so you get a regular Galilean multiscalar. And that has sigma equals 2, but still 6 derivatives. And then as I try at any derivative order to go to higher sigma, everything that you try fails. There's nothing. Nothing out here. By the way, there's one thing down here. Sigma equals 0 and no derivatives is simply just phi to the 4 theory. But that's basically kind of a trivial point. Another trivial point we found was if I tried to impose sigma equals 1 with 4 derivatives. That's what I had when I didn't fully fix my DBI, but before I had DBI. When I didn't fix the last 6-point term, I found I could always have sigma equals 1, but there were no fixed terms. And that's because the class of terms here, they can always be written as something with a derivative on every field. I can always choose to write down such a theory. And that doesn't fix any relative coefficients. It's trivial because of the shift symmetry with the constant is manifestly there. These will always have sigma equals 1. So this thing is trivial. Likewise, at 8 derivative order, I can always put 2 derivatives and write a function of interactions with 2 derivatives in a field. And then I trivially get the enhanced symmetry to sigma equals 2. So that means that in terms of softness, anything with more derivatives, meaning that it lies to the left of this line, is trivial. And so this gives a very special thing, which is that there is a unique set of theories, a sort of little set of islands in the space of exceptional theories that have these enhanced soft limits, vanishing soft limits. And these are the exceptional field theories. And no matter what you try, that's what there is. You can, of course, have DBI multiple scalars, Galileans with multiple scalars. You can have different kinds of not-linear sigma models. I use them with that joint field, but there's also things like CP1 models and so on. But you can bootstrap them down and with very little input, figure out exactly what they are based on this soft limits. So this was first worked out in a reference that I'll give you, that I've given you on the wiki page. And that was first written down a diagram like this. Anyway, there's some reference there for you. So this is how far we can go with scalar fields. And the next thing we'll have to do is, of course, study particles with spin, and that's what comes tomorrow. So this is where I'll end for now, and I'm happy to try to answer questions from anyone who's ready to hang out.
Thanks, Henriette. Okay, so maybe let's have a few questions now. The next official event will be, I guess, 1:30 Mountain Time. There's a social lunch on GatherTown. There's nothing official between then. So just, yeah, let's have some questions now on Zoom.
Can I ask a question? Just to make sure I'm understanding like the overall logic of what's happening here. So I guess like when you write down a Lagrangian, you go out into the world and you do your experiments and you see like what symmetries there are, what representations, blah, blah, and you write down all the terms that are consistent with those things. So here you're doing the same thing, right? You're going out into the world and doing your experiments and then writing down all the amplitudes that are like concordant with the things that you see, right?
In a sense, the logic is a little reversed. So often if I'm thinking about it phenomenologically, I would say I want to model some particular phenomena. So I write down, say, my standard model plus something that gives me proton decay, some high derivative operators. And then I have my specific model, maybe with some free parameters, and I go ahead, I calculate observables, I compare it with some exclusion plots. And but all in this context, I have a specific model with specific parameters. The approach that I'm taking here is a little bit the reverse. It's asking the questions, where in the space of all quantum field theories do theories exist with certain properties? So a priori, it's not completely obvious that the space of theories that have, say, vanishing soft limits that can arise from spontaneous symmetry breaking, even if I don't even know any details of the symmetry breaking, that these are so constrained that this is what you can have.
Okay, I guess like sort of with that, I was just a little confused why you were imposing what sigma you wanted. I guess that was to show us that like if you choose a sigma, then your theory is extremely constrained, right?
That was with this kind of plot in mind, that I can go through all the different points in this diagram here and ask, does it exist? And when it fails, I know for sure that no matter what you try to do at the Lagrangian level, there's no way this can ever happen. And this might be a little surprising. Like there's no way you can enhance the symmetry so much that you get these extra vanishing theories. And what is also a little surprising is just because, say, for the DBI case, it's kind of surprising that it's unique. Maybe when you have the physical picture of the brain in mind, it's like, of course, that's what it has to be. But it is actually truly unique from just very, very simple assumptions. Another case where this can come up, so let me mention two contexts. So in context of phenomenology, you can take the approach that there's some particular model with some particular couplings that you choose to study, but not others. And then you can study the heck out of that and see what compares with experiment. You could also take the approach of saying, I want to characterize all standard model effective field theory couplings that possibly exist and understand any possible relations between their couplings. And then I can go out and compare. But now I have a vast space, but I need to find an independent basis of these operators. And to do that, amplitudes methods are very powerful.
Mhm.
And that's what people are starting to use for that point of view. That's one example. A second example is to understand things like accidental symmetries in a sense. So this is from a more formal point of view. If I go out and say, ask the same questions. Here we asked getting a theory with sigma equals 1 for a single scalar field. And we ended up with DBI and it was nicely enhanced and so on. What if I ask it with 2 scalars? It turns out that if you insist on vanishing soft theorems, then you automatically get that there has to be a U1 symmetry. You don't assume it, but it turns out that if you insist on the vanishing of soft theorems, you cannot do it without having an accidental arising U1 symmetry. And the reason then you can then figure out why you got it was that a single scale, a theory with exactly 2 scalars, you can always group them into a complex scalar, but the fact that they always appear that can only be even point at the leading order, that you never break the symmetry at the leading order 2 derivative level of the theory, is because it's actually a CP1 model, which is SU2 mod U1. So SU2 mod spontaneously broken to U1. There can't be anything else with 2 scalars. And it's kind of nice to have these uniqueness theorems and see how these symmetries just come out. If you try to enhance the symmetry, it turns out that there's a global SU2 symmetry. If you enhance to n equals 2, there has to be a certain SU2 symmetry also arising. So these kind of things that you observe in specific models that have to be there turns out to be sort of bootstrapped. So the relation here is much more in the spirit of the conformal bootstrap, where people go into the landscape of QFTs and ask, of CFTs, and ask, narrow down on the little islands of the 3D icing model. We do it similar here, but it's a little more discrete sense because we can only be at discrete points in this landscape of exceptional field theories, but you can really narrow down things.
Oh, that's super cool. Thank you.
Can I ask a question? I guess you said in the beginning you won't be talking about loops, but for DBI and these exceptional field theories, are the amplitudes still soft at the loop level, or?
Oh, very good. So what happens at loop level? So as Goldstone modes, these remain massless at loop level.
Yes.
At loop level, since this is an effective field theory, when I go to loops, to be consistent in my coupling counts, I also have to include higher derivative operators consistently. And once you go to the high derivative operators, I think you should in this case preserve the shift symmetries, but you may have to include both in order. So you may have to include counter terms to get this to work out correctly. That will be typically what happens in these contexts.
Okay, thanks.
Other questions?
More questions?
I have a question. So assume that you see something like sigma equals 4 in nature. What is your go-to solution? That locality is what's breaking down, or is it some other axiom that usually breaks down?
So sigma equals 4 would have to be very, very strange. One reason you could argue from a Lagrangian point of view it doesn't exist is that you could never make even your kinetic term invariant. So yeah, you can see what breaks. I mean, I don't think you're going to see sigma equals 4 in nature, I would think, but you would have to somehow get around the locality arguments here, I guess. Or you
And I suppose I'm asking, why are there bounds? What are the physical reasons why we get to bounds?
Well, so if I think about these symmetries as the softness arising from shift symmetries, then up to things like field redefinitions, this is kind of what it looks like. So this gives me sigma equals 1. If I have this, I get sigma equals 2. If I have that, I get sigma equals 3. So I would need something that's even crazier than this to be able to get to sigma equals 4. So the first thing I have to worry about is making a kinetic term invariant. And in all these contexts, I'm looking at a small field expansion, so I would have a canonical kinetic term. Of course, you can ask if I can do other things too. I don't think so, because eventually to do these calculations, you have to go to a small field expansion. Anyway, sorry, this term is clearly in, the kinetic term is clearly invariant under the constant shift. The second term ends up being invariant because it gives a total derivative. This term is invariant only when this tensor that sits in front is traceless, but you can't make this guy invariant. And so this is not maybe a fundamental answer, but at least it's a practical answer that from the point of view of the kinetic term, I just can't even make it invariant under sigma equals 4. So that I shouldn't be able to have any interactions that do it either. But the soft bootstrap is a very clean way of showing that it can't happen. But from a fundamental point of view in nature, it's very bizarre to have even this enhanced symmetry. As I said, I can understand these two from the DBI action because they arise from the spontaneous broken translational and rotational symmetries. But I don't think we have a fundamental understanding where even sigma equals 3 comes from. There's a sort of little a less clear paper that has some arguments, but I don't think I could even reproduce them. So I don't have a geometric way of saying where sigma equals 3 even would come from, much less sigma equals 4.
Can I ask a short follow-up?
Sure.
So, there's things in 4 dimensions like theories of class S, which are non-Lagrangian field theories. I guess they would follow from 62, 0 in some sense. So these are all non-Lagrangian field theories. Would these be covered under the soft theorem technology that we're using here, or could these have other soft behavior? So
if they have, good. So
and we seem to be depending on Lagrangian technology here a bit.
So in all this, I'm basically using tree-level techniques, right? And the reason I can justify doing this is that I'm in a low enough energy regime that all these couplings, when I just call them G4, what I should really think of it as is some G4 with some dimensional suppression. So this would be dimensionless G4 bar, but there's some UV scale that enters, and as long as I'm below that scale, I have a fine perturbative expansion. So the question would be if in a non-Lagrangian theory, it has some limit in which there's an EFT description of it that I could use to use these methods, or at least give something that means I could use tree-level methods, because otherwise I have much less of a handle on the problem.
That makes sense. Thank you.
Okay, I think let's.
You could, so maybe just briefly, you could ask if you could go on a Coulomb branch, if they have a Coulomb branch, and then do a low energy expansion of, say, dilaton modes in that context. That might be a way you can get.
Okay.
I don't mean to cut this short. I think this is great, but I think also people should have time to get lunch and stuff. So maybe if you want to hang out, Henriette, and then people can feel free to leave, or you can also leave. But yeah, but let's just thank Henriette again, and the next thing is at 1:30 in Mountain Time on GatherTown.